Hi, today we're going to be talking about probability. Probability is a measure that we use to tell how likely an event or an outcome is. For example, if you've ever watched a weather report on TV, you might have heard the weatherman say something like, "There's a 10% chance of rain today." We use probability anytime we want to know how likely something is to happen. For example, how likely is it that one player or team will win the game? How likely is it that I will win the lottery? How likely is it to rain or snow today? We can also use probability to determine how likely a baseball player is to hit the baseball when he's at bat. We often write probabilities as fractions. When we do this, the numerator shows us the number of ways an event can occur, while the denominator tells us the number of possible events that could occur. Probability can also be expressed as a percentage, as you saw in the example with the weather report. Let's look at a few more examples and do some practice.
Many students were asked about the probability of passing in their mathematics paper. Let's understand their responses. The first student was very sad and said that the probability of his passing was low. The second one was really happy because he felt that the probability of his passing is very high. The third kid was a little confused. He says that his probability of passing is somewhere in between. So the probability just tells you how likely it is for an event to occur. Here, the event is passing the exam. In the first case, the likelihood of passing is not very likely. In the second case, the likelihood of passing is very likely. And here, the likelihood of passing is somewhere in between. But none of them are sure. They are just telling us what they feel and what is the most likely outcome. That's probability.
Of frozen yogurt. So every day after school, you decide to go to the frozen yogurt store at exactly 4 o'clock p.m. Now, because you like frozen yogurt so much, you are not a big fan of having to wait in line when you get there. You're impatient. You want your frozen yogurt immediately. And so you decide to conduct a study. You want to figure out the probability of there being lines of different sizes when you go to the frozen yogurt store after school exactly at 4 o'clock p.m. So in your study, the next 50 times you go to the frozen yogurt store at 4 p.m., you make a series of observations. So you observe the size of the line. So let me make two columns here. Line size is the left column. And on the right column, let's say this is the number of times observed. So times observed. Observed. All right. Times observed. My handwriting is OBSEERVED. All right. Times observed. All right. So let's first think about, okay, so you go and you say, hey, look, I see no people in line exactly, or you see no people in line exactly 24 times. You see one person in line exactly 18 times. And you see two people in line exactly 8 times. And in your 50 visits, you never see more than two people in line. I guess this is a very efficient cashier at this frozen yogurt store. So based on this, based on what you have observed, what would be your estimate of the probabilities of finding no people in line, one people in line, or two people in line at 4 p.m. on the days after school that you visit the frozen yogurt store? And let's say you only visit it on weekdays where there are school days. So what's the probability of there being no line, a one-person line, or a two-person line when you visit at 4 p.m. on a school day? Well, all you can do is estimate the true probability, the true theoretical probability. We don't know what that is, but you've done 50 observations here, right? This is, and notice this adds up to 50. 18 plus 8 is 26. 26 plus 24 is 50. So you've done 50 observations here, and so you can figure out, well, what are the relative frequencies of having 0 people? What is the relative frequency of 1 person? Or the relative frequency of 2 people in line? And then we can use that as the estimates for the probability. So let's do that. So probability estimate. I'll do it in the next column. So probability probability estimate. And once again, we can do that by looking at the relative frequency. The relative frequency of 0, well, we observe that 24 times out of 50. And so 24 out of 50 is the same thing as 0.48. Or you could even say that this is 48%. Now, what's the relative frequency of seeing one person in line? Well, you observe that 18 out of the 50 visits, that would be a relative frequency. 18 divided by 50 is 0.36, which is 36% of your visits. And then finally, the relative frequency of seeing a two-person line, that was 8 out of the 50 visits. And so that is 0.16, and that is equal to 16% of the visits. And so there's some interesting things here. Remember, these are estimates of the probability. You're doing this by essentially sampling what the line on 50 different days. You don't know, it's not going to always be exactly this, but it's a good estimate. You did it 50 times. And so based on this, you'd say, well, I'd estimate the probability of having a 0-person line is 48%. I'd estimate that the probability of having a 1-person line is 36%. I'd estimate that the probability of having a 2-person line is 16%, or 0.16.
Chance of winning each match. One way to see that is to list all the possible combinations you could get by rolling 2 dice, and then count up the ones that each player wins. These are the possibilities for the yellow die. These are the possibilities for the blue die. Each cell in the chart shows a possible combination when you roll both dice. If you roll a 4 and then a 5, we'll mark a player 2 victory in this cell. A 3 and a 1 gives player 1 a victory here. There are 36 possible combinations, each with exactly the same chance of happening. Mathematicians call these equiprobable events. Now we can see why the first glance was wrong. Even though player 1 has 4 winning numbers and player 2 only has 2, the chance of each number being the greatest is not the same. There is only a 1 in 36 chance that 1 will be the highest number, but there's an 11 in 36 chance that 6 will be the highest. So if any of these combinations are rolled, player 1 will win. And if any of these combinations are rolled, player 2 will.
It was sunrise at the crossroads, a glorious day to see, when a cowpoke came riding up on a horse and looked down the road called 3, stopping to think about someplace else. In probability, it was likely, yes, though it wasn't for sure, that this cowpoke would spin a 3. The sun climbed up to high noon. Another cowpoke said, "Gee, with an outfit like mine, it's certainly clear. It's unlikely I'll visit 3. A dry wind whistled. The cowpoke spun more than once to be on the safe side. But the answer was clear. This lone cowpoke down the someplace else road would ride. Then later that same afternoon, one mule from a mule team clomped in. One look at this cowpoke would make it quite clear that 3's an impossible spin. The spinner could spin all day, all night, but one thing was easy to see. This cowpoke was headed to someplace else, but never, oh never to 3. As sunset arrived, one last cowpoke rode up a strong horse's back. The chances that 3 on the spinner would be were certain. And that is a fact. Impossible clearly was not a word this cowpoke would ever use. A few quick spins made sure that 3 was the only road to choose.